Hi, everybody. How are you? Good. I'm glad to hear you're doing well. Hi. So, if you have a moment, just go ahead and download the notes and the assignment for today. Okay, so if you get a chance, please check Unit 7. Also, I posted the paradox information. I want you to take a look at it. I'll work on some fun game for us down the line when we do the review. So we'll do a little bit of the paradox game, so it will help you review later on too, okay? So now, okay, so I'm gonna share screen real quick. So I'm gonna clean up some of the program for your lab. I think previously I'm using a different STL, and it was given the students last semester a little bit of an issue when they're not using REPL. So I'll post the lab possibly maybe tomorrow. So I'll clean that up and I'll share that with you, okay? And then we will do the search and sort algorithm in C++ this week. It might look kind of similar to some of the things that you're doing or you did in CIS7C if you have taken the class or if you're currently in the class. But we'll talk about the manual calculation of the search and sort algorithm today. Okay, so this week we're going to cover Chapter 10. You will find the notes located here and the assignment here. So when I was, let me fix the date real quick. When I did this last time, this was when we fully went online last semester because of COVID. So there were some challenges with the student trying to adjust. So this, we will get everything done by the 10th. Okay. Okay, so today I want to talk a little bit about search and sort and how we would be able to handle that when we're looking at the programming side along with the mathematics. And there's the probability paradox, which has the Monty Hall and Khan economy. I included the link, and also information about deal or no deal. I will share the solution for 10. I have a list of the students that got the extra credit. You guys did really well. About 50% of the class actually attempted the extra credit, which is very impressive, more than last semester. So I will share the solution for that. I will enable it by lab this week. Okay. Okay. So let me see. Sorry, let me reopen my notes. So this week we're gonna talk a little bit about algorithm, and we touch on it briefly when we're doing lab last time, when we're looking at the fundamental and really breaking everything down to the smaller pieces to solve the problem. And from here, what we're gonna get into is recursion, a little bit more on recursion, and also looking at relationships with containers and looking at objects with the programming side. So this week, in chapter 10, it talks about algorithm, and the majority of you are in computer science, so you'll find that this is what we really implemented in programs to be able to solve the bigger problem for businesses, and you know, in a lot of cases now we can incorporate this to really solve the bigger problem using machine learning and such. So algorithm is really a set of rules so that way we can follow when we calculate or solve a problem. And in programming, we really break that down into the smaller parts to really tie all of this back into a larger application. I was talking about this in my Python class yesterday, how to really derive or define a function that solve subproblem and then be able to build on that to solve the larger problem as an objective. So in this week, we're going to talk about searching is when it's going to seek a key based on the type of algorithm that you implement. And then we're going to talk about sorting when it's going to organize your data in a specific way. Okay, and so there are different types of traditional algorithm we're going to touch on today. So our goal is to look at a collection, whether it's a set or ultimately in programming, we will look at this as a container that would have values. So for example, it would have integers or it could be prices. And you see this in real world application in such that you use, you know, search engine all the time, or when you're using a database to search for a record, or when you're looking for a piece of data in a collection of data. So we're gonna find a particular object in the collection, and we want to implement the steps on how to recognize that object, whether it exists or not, okay? So today we're gonna take a look at the algorithm for those steps. Now, when you are searching, you're really trying to look for the key values. So for example, I have 1 through 100 and I'm looking for number 51, right? And we can implement the step on how it would search through that collection of data, whether we're doing a linear search where it's going to look at every single item in that container, or we can break it up into subsets and then looking at the subset each time. So that way it might streamline the process and increase the performance or give you more efficiency. So pay attention that we need to give it a key value, and based on that, it's going to search the data and to be able to recognize if that object can be found. So likely you would see on the elementary level, we would see an array, which is a container, and we can assign values in such array. And you can use vector. Yesterday when I was teaching Python, I talked about double-ended queue or deck, and you might hear that in your data structure class, where we can go on both ends to really search or seek an object where it would be more efficient. But on the lower level, we would say, okay, well, we have an array and that's a container, and we can assign value. And when you're using a container and you want to iterate through an array using the index to identify, right? If we do it linearly, we would iterate through each index to identify that actual key value, okay? So there are different type of algorithms we can use. Our goal in search is to find the key value in our collection. So in the first part, it talks about an unordered linear search, meaning that you have data that's not pre-sorted. It is unordered, very much like a set. It would have unique value, but there's no ascending or descending sort, meaning that we don't go from low to high. It's not pre-organized in a certain manner. So we simply input the data and we don't organize it, and we would tell the system to search through it. So in this case, if you look at the example, and unlike programming, right, our index here start with 1. In programming, we would start with index 0 for the first element. So let's say in the first element we have 34, the second 16, and so forth. So this is our data set. Now we are seeking our key, which is number 11. And in this container, it is at the 4th element, okay? So when it's going through this search, it's when the search is being processed, what it's gonna do is when it's doing it linearly, it has to examine every single item until it gets to the key, okay? In such case, that if the key is not found, then it has to go from the beginning to the end, right? So let's say if I'm looking for the number 100 and it doesn't exist in my container, it has to look through every single item until it gets to the end, and it will give me the result that it cannot find the value. Now, in our example, we're looking for the number 11, so it's gonna search through, so we're gonna iterate through the first element, the second element, the third element, and then when we get to the 4th element, it's gonna find the value. It says that 11 is found, okay? So now at this point, what it's gonna do is it's gonna stop here because it finds a value. Now, when you create your program, as we previously explained this, right? We look at the worst case scenario, meaning that what if that number doesn't exist? Then it has to iterate through the number of elements, your length of array, right? Which is n. That will be your input, okay? So in our case, the performance of this algorithm is considered to be the examination count. And that would be the measurement of the performance in that algorithm. So it's dependent on the number of input when we're looking at linear search, okay? And in this case, because it's not ordered, it's not organized, right? It has to seek through every single one, okay? Any questions so far? Okay, so let's take a look at your assignment. So from here, we have to see the differences and the similarities between the unordered and the ordered linear search. So let's talk about that first. So in the ordered linear search, which is on page 1, it tells you that we would have a pre-sorted set of data. So your array is already sorted. So let's say that you have the user input the values, right? And you create a dynamic array where it would be flexible to the number of input that the user has entered. Then what you can do with the ordered linear search is you would have a function that would sort that array. So we would have to incorporate the sort for the ordered linear search to work appropriately. So now it says that one need not necessarily search through the entire list to find a particular object to determine whether it exists or not, right? So let's say that we organize it ascending order, going from smallest to highest. And what we can do is that we can say, okay, let's look for a key. Let's say that we're seeking number 34, which is the fifth item or the fifth element in that array. So the search can now be terminated early once it's determined to be that it's sought. So in this case, what we can do is, there are several ways to approach this. We can set up the midpoint of that array and say this is the median. And if your key is higher than that median, it's going to look at the last half. Okay, linear wise, it's still going to look through the items in the last half to really find that particular key. So we can simply use the comparison operator and we can say, okay, well, if we're going from low to high, what's the midpoint for that array? So at this point, 16 is really the middle, right? So we can identify that that's the middle, and then if we're looking for a key that's higher than that, then we can send it to the last half of that array and it would look through the items for that. So as soon as it gets to the next element after the midpoint, it's going to say, is 34 equal to 34? If that's true, it's going to return. Okay? Then here at this point, what we have is it's going to stop and it's going to say it found the key and it's in the fifth element. Okay, so that's one approach in how you can improve efficiency with the linear search, where instead of an unordered linear search, we have to go from the beginning until the point where it finds it, if it finds it. Where in this case, we can still have it linearly look, but we can point to, as it is already pre-sorted, we can point to if it's that midpoint is going to be lower or higher. Okay, so different programmers will have different approach, and you can see how people actually create their linear search. But in such case, this one, it would quit as soon as it finds it. It would terminate as early as it's determined that the number is sought. Okay. Now, that would be usually less than the entire array, or what we would see with the unordered. Okay, so for the first question, we can simply state that an unordered linear search, in order to determine that the object does exist in the collection, it needs to search through the entire collection. And in worst case scenario, that object doesn't exist, right? Then it still needs to go through the entire collection. Now with the ordered linear search, since it is sorted, right, it would find it for the entire list. To find that particular object, it would need to scan the array from left to right, and would terminate as soon as it is found. So if you have it pre-sorted, a quicker way, like I said, to set up where it would be compared, if it's still smaller, then it's going to move to the right of that, and it's going to keep going until it finds that matching key. Okay, so we would have efficiency with the ordered linear search compared to an unordered linear search. So that's the main difference, is that it's more efficient in that it doesn't have to search through the entire array. Okay, but it's still going to examine the item, right, linear wise. That will be the similarities. Do you have any question? So for quiz and test, make sure we understand the difference between an unordered and ordered linear search. Okay. So now, after this, right, it goes into the chunk search. So in the case where, you know, going back to the order linear search, in the case, or if you're searching for a value that doesn't exist in that array, in that container, what will happen is that it needs, so when it gets to, so let's say that we're looking for number 13, which should be here, but it doesn't, it's not in our array. So what happens is we know that 16 is the midpoint, okay? Then when it looks at this, it's gonna say, okay, is it lower or higher than 16? If it's lower, it's gonna try to go to the left. And when it sees 12, it's gonna say, oh, that's not 13, right? And then it's gonna quit. So it's gonna give you the output, 13 is not found. So with that, when we look at the programming side, we would implement the control statement for that, right? When we compare, if it's true, then it's gonna iterate either left or right, okay? So if we compare, if it's greater than 16, we're gonna have it iterate to the next, to these right here. It's gonna find these, try to see the key, if the key exists in the next one. If it's lower, we can try to have it seek to the left. And as soon as when it gets here, it's going to try to look for 13. And since 12 is lower than 13, then it says that 13 is not found. So we definitely is a better advantage using the ordered linear search compared to unordered linear search. Okay, any question? So in this textbook, they use chunk search, but you often hear the name jump search. Okay, so this is equivalent to jump. And you might have seen example of jump search before, but if you haven't, we can talk about the actual mechanism on how it's searched. So in jump search, the chunk, meaning that it's going to break it up into subset or sublist or groups, smaller groups inside that array. Okay, and we can determine the chunk size based on the number of input. Okay, so in our example here, we have 1 through 8, right? The first through the 8th elements, and these are the assigned values. Let's say that we give it a search key. Let's say that we want to look for number 34. Okay, we're going to try to seek number 34 in this array. So based on this, what it will do is it will section, it will divide up different chunks inside that array, the subgroup. or the subset. Okay, so how do we determine that? Well, if there is 8 elements, it will take the number of element, the number of input, and we can do a square root to really see how that's going to be divided. Okay, so what that will be is like, it's going to be roughly, right, chunk of 3, and chunk of 2. So we're going to ceiling it a little bit. We're going to round it up a little bit. So what it's going to do is, first it's going to take a look at the highest value in that first chunk. So since 34 is still higher than 12, it's going to move to the next chunk. And it's going to say, okay, it has to exist in the second chunk because, right, it's not in the first chunk as the highest value is 12. And in this one, you have to have it pre-sorted. Okay, so we should start it with a pre-sorted array, so that way we can compare as in what is the highest value for each chunk, so it can move directly to the right chunk when we program it. Okay, so here what we see is, okay, the highest value for the second chunk is 37, so it knows that it's in the second chunk and it's going to find it there. Okay, and it's going to disregard the rest. So with this is that we can see that if we break it up, if we divide up that container into the subset, it can be more efficient in seeking that key value by looking through each of the subset or comparing the highest value for the subset, so that way it can eliminate that. Okay. So as we mentioned, that since 12 is lower than it, it's going to move to the second chunk, and then it's going to try to compare. So 34 is greater than 12 and 34 is less than 37. That's the highest value in the second chunk. Then it's going to know that it's in the second chunk. Okay. Any question? So as you take a look at this, you should ask yourself, how would I program this, right? After we initialize our array, we can have a function to sort it in the case it's not sorted. Once we have it sorted, we will have it size, we will determine our chunk size, and then based on that, we would implement the control statement to compare, right, what's the highest value in each chunk, and then be able to have it move to the appropriate chunk. Okay, any question? Okay, so in the case where if we have a key value that's not to be found in the array, it doesn't exist, right? As we talked about with the unordered linear search, it's going to go to that midpoint. It's going to say, oh, 33 is not there, right? Because between 16 and 34, 33 doesn't exist in the array. So it would give you that. With the chunk search, it would have, so to be executing this, what we would have to say is it's still going to point to the chunk. It's going to say, oh, you're looking for 33. It needs to be in the second chunk. And when it looks through the second chunk, if it's not there, then because it's going to compare 16 and it's going to compare 37. As 33 doesn't exist, it's going to tell you it's not found. Okay. So any question? Okay, so let's answer the next question. The similarities and differences between linear and chunk search. For the chunk search, the collection is divided into chunk or subsets, what we call C, which is equal to the square root of the number of index, or n. We can say square root of n. And the search key is compared to the maximum value of the first chunk. If the search key is greater than the maximum of the first chunk, the second chunk will be evaluated, and so forth. With the linear search, if we're looking at the unordered linear, it iterates through the entire array, or it iterates through the array one by one. With an unordered linear search, the elements are compared and it terminates as soon as the element is found. So it needs to find a midpoint, compare the element, and then it's still going to evaluate every following element from the half point. Then it's going to terminate as soon as it's found. If it doesn't find it, it has to go to the end. Okay. So with this, we can simply use a loop to have it doing the comparison and check every single time with each of the following element. Okay. So when we look at efficiency, chunk search or jump search is definitely more efficient. Okay, so let's calculate that. Do you need that to be, it's in your notes, so you can, and you don't have to write by verbatim. I just took the pieces from the note and then I added there. Okay. So we saw some of this in the lab already. The last couple of labs we touch on this when we're looking at the amount of time for a certain algorithm to run, T of n. Okay, and we would estimate it based on the number of operations for that algorithm. So it is common to consider worst case scenario when you're looking at how that program is ran. And in some cases, they do measure the average, but that's less common. Okay. And when we're referring to big O or big O notation, we're really saying in the order of, right? And every algorithm would have specific big O values, so, or formula. So here we go. So when you're looking at creating the solution, right, or building the algorithm for your program, you need to really think about the 4 steps. First, we need to use the step-by-step procedure to solve the problem, so design an algorithm. And within that, what we will see is, if let's say it's a linear search, we would have to incorporate some kind of looping, some kind of comparison, right? Some sort of sorting mechanism. So there would be a step-by-step procedure that's required to solve that problem. Then the second things we need to consider is that we got to make sure that we analyze the accuracy and the efficiency of that procedure. So as you go through and you said, okay, well, this is going to be efficient based on the objective for this program, then we can implement the procedure using programming language, C++, Java, Python, you know, you name it. And then we can test. Okay. So here are some of the factors that you need to think about when you're building your algorithm. The size of input, okay, n, your n value. So if you have a very large array or large container, let's say that it holds 1,000 elements, that's different than an array that holds 10. Okay, so that's also a factor that plays into this. The algorithm that you use to solve the problem, and this is where tech company really evaluate your skills, right? They tell you, okay, write a search algorithm. So this is where you can say, okay, should I do a binary search? Should I do a linear search? So the procedure that you implement to solve the problem speaks your skills, okay? Mathematically and programming wise. And then next is when we would implement it with the language. And the quality in implementation is that your code needs to be tight code, it needs to be clean, it needs to be fast, right? And then lastly, one of the factors that plays into this is the computer that runs it, okay? The type of processor that it has, whether it has adequate resources for your application to run. So, you know, if it's a slow machine, of course, the performance is going to be poor. So we need to think about worst case analysis. And here it talks a little bit about that, where what would be an average or a typical input, how fast is fast, right? So we always evaluate our program based on worst case running time. Okay. Okay. So here again, coming back to linear search. So when you're looking at linear search, your TFN is n, the number of input, because it's going to look through every single element. Whereas the chunk search, we need to implement the chunk size. So in the program itself, you need to tell it, take this array and chunk it down to this size. Okay? And we need to be able to calculate that size. So in the case where if your chunk is small compared to the larger chunk, of course it's going to perform better. It's going to be faster, right? So the standard with this, as you can see, is that our chunk size is going to be a square root of the number of inputs. So if you have 1,000, we can chunk it, right, to a number of elements. So that'll be a square root of 1,000. Okay. Any question? Okay. So when you're looking at, for the chunk or the jump search, T of n is equal to n divided by c plus c, right? As you do, when you implement the substitution for this, you would have the comparison at 2 times square root of n. That would be the number of comparisons that it needs to perform in order to get the right, to find the key. Okay. So let's solve some problem now. Oh, yeah, I forgot to answer 3. So what's the purpose of worst case analysis in analyzing algorithm? It aims to determine the slowest possible execution time for the algorithm. It is useful because it tells you no matter what, the running time of the algorithm cannot be slower than the bound derived. Okay. So when we say that if it's a good worst case running time, that will always be fast in comparison to on average or typical input. So the average case analysis aims to really determine how fast the algorithm is on average, which is a typical input. So if the worst case running time of an algorithm is quite slow, that will be typical. Okay, so you can just indicate the first part, that's good. Okay. It aims to determine the slowest possible execution time for an algorithm. And it's useful because no matter what, the running time of the algorithm cannot be slower than the bound derived. Because you don't know what other factor will play from the user side, right? We would expect that the user might not have the best system to run your application. Okay? They might not have the fastest computer. Okay? They might not have, the system might not have appropriate resources. So we want to use the worst case analysis in such that it cannot be more worse than what's already bounded. Okay. So in the next question, question 4, it asks you, when searching through 2,000 elements in a vector, assuming that the system takes 0.5 nanosecond to search through each element, how long would it take to search through the entire vector? So if we're doing an unordered linear search, we're using linear search, we simply use the value of n, which is 2,000 element, right? And since it's looking through each element, it takes 0.5 nanosecond, half of a nanosecond. Then we would multiply 0.5 times 2,000 gives us 1,000 nanoseconds. And if you do convert that, that will be the value for the minutes. So if you put the answer as 1,000 nanoseconds, that will be okay. Any question? Is there another way to sort an unordered collections beside the linear sort? We'll talk about sort. There are other ways. We'll talk about sort. So after this, you should be clear on how you would be. And then for the lab, you will be doing search and sort this week. So you will experiment with some of it, not just using linear. Okay. Sort is in the last half of this. Okay. All right. So for number 5, it asks you if an application uses jump search to find matches in 100 elements in an array, what is the chunk size in the worst case scenario? okay? So our n value is 100. So you simply take that 100 and you would operate a square root, okay? So in programming, that would be easy, right? You initialize your n value at 100. And then if you implement the CMath STL, then you can do the square root operation on that to get your chunk size, your C. So in this case, when we're using 100 elements in our array, we would have 10 for C. Your chunk size is 10. Any question?
What would you do if it wasn't like a perfect root? So how would you determine I then?
So, and you know the computer doesn't search half of an element, right?
Yeah.
So you would ceiling it. You round it. There's, you know that in programming language, you can have it round up or round down, okay? And so you weight the this and that. So for me, I would, when I chunk it earlier, you remember when we do the square root of 8, it's not perfect. It's not 9 or I'm sorry, 100. So when you do the 8, so it's going to need to chunk a 3 and a 3 and a 2, okay? Because it doesn't search half of an element.
I see. So until it reaches like the last satisfied part, it'll basically just do the regular I, the root rounded down until it reaches the last chunk.
So the whole point is that we don't want it to go through every chunk. That's not the point. The point is to find the chunk that it will find the key.
Okay.
So when you chunk it, what you're doing is you're putting a marker on the value for the previous chunk. You get what I'm saying? So let me flip back to the notes so I can show you an illustration. It's a lot easier to see. Okay, so let's go back to the example from the beginning real quick, okay? Like the one with the 8, okay? So the whole point is not to have it evaluate every single chunk, but the whole point is to put the marker on the highest value for the previous chunk. Okay, so in this case, we know that there's 8 elements, so it needs to do a 3, and a 2. So we at the third element, we know that this value is 12. It needs to skip this chunk and it needs to move over here. So when we're seeking 34, since there are 3 elements there, it's going to look at the middle.
I see. So if it's not like an even, it won't ever mark the last one because it'll just compare it to the previous chunk.
Yeah. So in the case where, let's say if I'm looking for 66, right? What's going to say is it's going to go here. It's going to say, oh, 66 is higher than the max of the previous chunk, which is 37. It's going to try to look here and it's going to tell you it's not found because the maximum value for the last chunk is 65. So therefore it's going to tell you, because with our if condition, that's going to be false and it's going to return. Okay.
Okay, that makes sense. Thank you.
Yeah, you're welcome. Other questions? Okay, so the whole point in this is for you to see it, right, as a step-by-step procedure. So when it's easier to write it once you see it mathematically. Okay, so we already determined the C size. So based on that, we would put the marker on the maximum value and point it to the right chunk. So that way we would have efficiency in our program. And then, so in the next question asks you, it says, when searching an array of 8,400 elements, and I use like even perfect numbers so that way it's easy for you to calculate, but the real world, it's not always like that, right? When searching through an array that contains 8,400 elements, how many comparisons must be performed for a binary search result? So before we calculate this, let's talk about binary search, okay? So you already saw how chunk search, and before we get there, this part of it right before the binary search on page 5 is important. It says if there's 1,000,000 elements, unordered linear search would require 1,000,000 element examination, worst case. With the jump or chunk search, it requires approximately 2,000 examinations in the worst case scenario. So if you're looking at, let's say we're talking about 1 nanosecond per, right, per examination, we definitely save time from one type of algorithm to another, like from linear to chunk. Chunk is more efficient, of course, okay? Because if you take square root of 1,000,000, that gives you 1,000. Then you multiply that by 2, gives you 2,000 examination for the jump or the chunk search. That's 500 times faster than doing a linear search, which it has, worst case scenario, it iterates through every single element. Okay. All right. And for binary, so we found the developers, they found a better way to approach search by, instead of using jump or linear, there's binary search. Right, as some of you are required to write binary search tree. So when I taught 17C, I make everybody write it for their project. And university, they require you to do that too, in C++ or Java, right? So in binary search, what we do is we take that array, we cut it down to half. So that would give you n divided by 2. Then we cut it down to half again. So that means n divided by 2 divided by 2, okay? Which is n divided by 4 or n over 4, okay? And then we keep sizing it down to half and half and half until it's small enough for it to quickly find that key value, okay? So in the binary search, it's determined that with the iterations, we would have log 2 of n would be the iterations that would be performed. So in such sense, we would no longer be able to cut it down to half again, right? It would be sizing down from half to another half to another half to another half until it's small enough to identify the key, which is log 2 of n, okay? So that would be the worst case scenario. And to calculate this, we can also say that that would be natural log of n divided by natural log of 2, right? Or you can punch in log 2 of n in the calculator and it will be able to give you the output as well. Okay, so in such that binary search would be much more efficient. So when we're looking at this table, we can look at the comparison. In worst time, right, linear search, that will be the number of input, which is n, and we simply compare the midpoint to the highest value. So key is greater or equal to the last, right, last half compared to this half. So in worst case, we'll have 1,000. Okay, for n as 1,000. With the chunk or the jump search, what we have is we can chunk it down, okay, and we would have roughly about 32. And then with the binary search, that will be n, log 2 of n, which is 10. Okay, so as you can see, it's much more efficient compared to the other search algorithm. Okay, so now this is important to note. Make sure, right, that the result that you see is, that means that we already have it pre-sorted. So when you build this type of algorithm, you gotta make sure that you have a mechanism for sort that's, you know, somewhere in your program before it even starts seeking. Okay, so we want to have a sorted order. Okay, so let's do the calculation for number 6. When searching an array that contains 8,400 elements, how many comparisons must be performed for the binary search to find result? So we know that our T of n is log 2 of n, which is also natural log of n divided by natural log of 2. So I think we come out to be about 13 comparisons. So we would have natural log of 8,400 divided by natural log of 2. Okay, so you would have about 13 comparisons. Now, if you do this in the programming, right? Yes, sometime you would have fractional, so you want to make sure that you, in C++, we want to make sure that we control that. Okay, so we can have it, we wanted to round it up. Okay, any question? Because if that's worst case scenario. Because if I round down like 12, right, we're losing the fraction of it. So we're not measuring it at worst case scenario. Okay, so this would be for the binary search. Okay, so make sure you know how to calculate. You're going to see a similar question like this on quiz and test, right? It will give you the number of elements and it's going to ask you how many comparisons for this type of search, and you have to be able to determine the result. So this one is for binary. Sorry for the large font. Sometimes that helps on Zoom, but when I did this on the projection in class, sometimes because they converted it to TV, so it was a little smaller. So I increased the font. Okay. So when we look at part B, how many comparisons needed to perform using chunk or jump search, right? So we know that our T of n is equal to 2 times square root of n. So our C size, our chunk size is 91. And we simply take 2 times 91, that gives us 182 comparisons. Any question? So when you're looking at binary search in comparison to chunk search or jump search, right? It's definitely more efficient. Okay. So we would usually go to binary search. Any question? Okay. And the last one is easy for part C, how many comparisons performed with the linear search. That will be 8,400 comparison. That's the same as your n value, right? T of n is n, which is 8,400. Much slower. Okay, so let's do the next one since it's going to be very similar to number 6. Okay, so when searching an array that contains 9750 elements, how many comparisons must be performed in binary search to find the result? So we would do natural log of 9750 divided by natural log of 2, or log 2 of n, log 2 of 9750, right? Which gives you 13 comparisons. How many comparisons need to be performed using the jump or chunk search? Then you would take square root of 9750, then you multiply it by 2. And then part C would be 9750 because T of n is n. Any question? Okay, so are we okay with search? So those are the ones that you're mainly gonna see, and you will see this in our lab this week. Okay, we'll do the chunk or the jump search, and then we'll do the binary search and also some sort. So you can see how that's done. Okay, so there are different types of sort. And the first one we're going to talk about is called insertion sort. So think of it like how when you're dealt cards, right? Most people, when they get dealt cards, they would pick up the cards and then they would organize it, right? Maybe high to low or low to high. And as they pick up the next card, if it's, higher than the previous card, they will insert it in between. Okay, so the first card is placed on the hand, the second card is compared to the first card and place it either before or after it. So it's comparing at a certain point. Okay, so that way we can start organizing, right, the value based on ascending or descending, depending on the objective. Okay, so here's the example, right? Here's your index from the 1st through the 8th. And as you receive the value, what we can do is we can compare to the last value and then organize it. So we would start with 34, right? Then when you get 16, you're gonna say, oh, 16 is lower than 34, so we would take it and insert it into the front of 34. Okay, now physically this is easily done, right? We just take the card and we move it into the front. But when you think about programming, values don't just get put into nothing, right? We have to move it to a location, and then from that location we're going to move it to the sorted location. So you have to do a triangular move. That's why I tell my student, So you have 34 and 16. We need to take 16 and place it in front of 34, right? So what you can do is, yes, you can set up another array, right? If it's less, you can point it to the index that's lower and then the other one. But if you're using variable, what's going to happen is you have to have a temporary variable. Move 16 to that, move 34 to the place of 16, and then take the temp content, which is 16, and put it into the first element. So you have to think about the movement, because the computer, it needs to have a space where it would store that value. We can't just swap it. So when we do a swap, it needs to be a triangular move. Okay? So now, with the process, if you take a look at this, this is a good picture. So first, we need to make a space in front of 34, right? Okay, that's face 0. And then what we want to do is we want to move 16. So we have to move 16 out, move 34 over, and then move 16 in front of 34. Okay. So this is called the insertion sort, because you insert the lower value based on the comparison of that last value, that first item element. So since this is higher, you would put it here. Okay. Then our next number, which is 12, right? 12, then you compare it with 16. Then you have to move 16 once placed over, and then you insert 12 in front of it. And then again, 11. Now when you get to 54, since 54 is higher than 34, then we simply put 54 after 34. Okay, and then 10 again, then we have to shift everybody right one spot and then put 10 in front of 11. And then 65, since 65 is higher than 54, we just move it behind 54. 37, right? 37, we have to compare, oh, is it higher or lower than 65? It's lower than 65, it needs to go before. So we have to get it to be right here between 34 and 54. Okay. So there's a little bit of manual comparison based on originally the first, right? And once you move that, and then you compare it with the first and the last again, and then the first and the last again, and so forth. Okay. Any question? So here it's saying that it's going to form n or k minus 1 elements in that array. So it's the one prior to the position of k. Okay. So the first array element needs to be examined. That's a must in the insertion sort. Okay. So when you do that, you just simply write if, right, this is greater than this, that value, then it needs to go to the right. If it's less, then we would swap it. Okay. Phase 2, the second element needs to be examined compared to the first. Therefore, that needs to have a swap. So with this one, we want to process it with a k at minus 1 element in resulting. Okay, so for the next one, let's do the insertion sort. Okay, so for question 8, it says use the below data and provide an explanation on how the insertion sort can be used with the given data. So we would begin with the numbers 6 and 87 compare. So I put that sort begins with the comparison of the second element to the first. If the second element is less than the first, the second element would be placed before the first element. If it is higher than the first element, it would stay in its place, and 87. So if 87 is higher than 6, 6 is placed before 87. So within this, our first iteration would look like this. And you don't have to create that table. I wanted to use that to show you what that would look like. So since 6 is lower, right, we're going to put it into a temp variable, right? And then we're going to move 87 to its place. And we're going to take 6 and we're going to move it into the first element position. Okay. And then we move to the next one. We're going to do 14, right? So here, this is after the first iteration. It looked like that. In the second iteration, 14 is compared with the first element. If it's less than the first, then it compared to the second, which was compared in the previous iteration. If it's less than the first, then it puts it into the first. But if it's not, right, it needs to compare to the next element and then insert it in between or after. Okay, so I put that if it is higher than the first and less than the second, it is placed after the first, before this, and before the second. If it is higher than the second, it is placed after the second. So with 14, we know that it is higher than 6 and it's less than 87, so it needs to go here, right? So what we do is we first compare. We say if 14 is less than 87, right? We're going to take 87, move it out to temp, take 14, put it into 87 place, take 87, put it back into 14 place. Okay. Any question? So with after the second iteration, we have 6, 14, 87, and so forth. Now, when we get to 60, again, it's going to do, is 60 less than 87? If it is, right, it needs to compare it with the first and the second element. So if it's higher than 14, you know that 60 needs to go here. So we move 60 out to temp, we move 87 into its place, and then we move 60 into it. So that's why it's K minus 1. Okay, so you don't have to do the rest of them. I just put the process continue with the next iteration. So once you understand how it's inserting based on the comparison, right? It starts with the first, compare it to the second element, and if it's not in order, it swaps. And then it does that again, compare it to the next one. Any question on insertion sort? No question. Okay, so let's talk about selection sort. Okay, so in selection sort, it would examine starting with the smallest one, and then we would do a swap. Okay. And the easiest way to look at this is we're gonna look at the table here. So the way we swap is gonna be n minus k plus 1 with the what swaps with the element in the position k. So again, we have the same set of data, 34, 16, 12, 11, 54, 10, 65, and 37. So based on this, right, this is your original set. Based on this, it needs to determine the minimum value. So we have to identify the minimum value, which is 10. Okay. And then what we need to do is we need to bring that 10 to the front because that's the least. Okay. So what we have to do is take that 10, put it in temp. Okay. Shift everybody over and then put the 10 in the front. Then on the next one, we know that the next least value is 11, and then it's going to move 11 after 10. Next value is 12, 12 after 11, and then 16, 34, and so forth. So what this will do is it's going to seek the lowest value. It's going to place that first, and then the next lowest value, put that second. But you have to swap. You have to move it. Okay, and there's no magic space in the computer. Like I said, you have to create a temporary position to move the data out and then put the one that's in order next to the least value. Okay, so this is a selection sort in such that it selects the smallest value and then the next smallest value and the next smallest value and swap position. Okay, any question? Okay, so let me put this on the next page so we can see it. Okay, so for number 9. So given the data, provide explanation for how selection sort can be used with the given data. So you have 41, 7, 12, 83, 3, 40, 16, 2, 71, and 6. Okay, so in the first iteration, it would examine the smallest value, which is the 2, and then we need to swap it. So we move the 2 out to the temp, right? Move the 41 to its place and then move the 2 into the first element. So 2 and 41 swap. Okay. Then in the second iteration, it selects the next smallest element of the n minus 1 elements and swap it in the position 2. And it would do that for the remaining. Okay. So when we look at this, after it's swapped with 2 and 41, 3 is the next least, okay? And it needs to move 3 to the 7 space. So we would take 7, put it in temp, move 3 into the second element position, and then put 7 in its position. And then we would go to 6. 6 is going to swap with 12. Okay. And then 12 with 83 and so forth until it gets all the way from low to high. Any question? So if you start listing the step on how some of these algorithm works, it's when you program it, it's so much easier, right? You can say, okay, well, here's where we branch. If this is true, this is going to happen. If it's false, this is going to happen. And sorting simply is a way that we can organize our data from low to high or high to low, right? When we do ascending, we go from low to high, 0 through 100, and then we can do descending, which is going to be high to low. Okay, so here's the next one. And you've probably seen this before, maybe not, but if you haven't, right, this might be new information. So there's a merge sort, and this is known as divide and conquer. We would break our list into 2 equal pieces, and then we would break it again into the smaller pieces. So you take the first list, you break it into half, okay? And then you would then break it into half again and half again until to the least. Then you would compare by merging it. So we would sort the sublist and then merge it. Okay, so we would break it into the sublist, very small sublist, sort it, and then merge it back. Okay, so the merge takes 2 sorted lists and then combine them repeatedly by comparing the 2 lowest element and sending the 2 smaller off to the next element in the combined list. So visibly, we can see this. So this is our original list. 19, 3, 12, 5, 7, 22, 18, and 4. Okay. We then cut it in half. The half marker is between 5 and 7. So on the left here, we have this list. 19, 3, 12, and 5. Then we break these 4 into half again, right? Sublist of 2, sublist of 2. Then we break it down to 1. Then we compare 19 and 3. 19 is lower, right? Move it in front of 19. 3 is lower than 19. 3 move in front of 19. 12 and 5. 5 is lower. Move it 5 in front of 12. Then we would take these 2 and these 2 and merge them. So you would have 3 and then 5, 12, and 19. Okay. And then you would do the same thing for the right side. 7, 22, 18, 4. Break it into 4. And then break it into two sublists. Then break it into 4, 1 sublist. Then we would compare 7 with 22. 7 is smaller, so 7 then 22. 4 with 18. 4 smaller, 4 then 18. So we would then merge it back. Okay, so first it breaks it into half and half and half until it gets to the one element. Compare it, then merge it back and compare, merge and compare. So that's why it's called divide and conquer. And it is faster than insertion and selection in worst case. So when we look at the comparison, the insertion sort is what you would see. That would be the worst in this would be n squared for our T of n. So if you have 1,000 elements, then you would have 10 to the 6. With the selection sort, it's also n squared, so you also have 10 to the 6. With the merge sort, you have n log n, which gives you 9966, and then the quick sort, which is 9966. Okay. Any question? So let's answer the next one. So you're given data 35, 19, 66, 4, 10, 28, and 6. Okay. Let me. Okay. So what we do is first we're going to take the list and we're going to divide it into half. So you have two subsets. 35, 19, 66, that's the left. On the right side, you have 4, 10, 28, and 6. So we would break the list into two equal pieces, and then we would sort and merge. Okay. So from the 4, we then break it up into two of the two pieces. So I have 30 and 5, 19 and 66, 4 and 10, 28 and 6. Then we divide it again into individual. So we first divide it into two subsets, then we make it into 4 subsets, then we make it into 8 subsets of one value each. Any question? So once you have it divided down all the way down to 8 subsets of one value each, then you compare. So we would first compare the 30 and the 5, right? So 5 and 30 would swap, merge them. Then we would have 19 and 66 compare. 19 is lower than 66, merge. Okay. And then again, we would do with 4 and 10, sorted merge. So 4 less than 10, then merge. 28 and 6, 6 less than 28, merge. Right. And then again, we would go from the 8 sublist back up to For sublists, we merge and we sort and then we merge. Okay, so after you divide it into the sublist, then you would order and merge. And then after this, we would merge these four together, and then these four together, and then eventually we merge all the 8 together after we order it. So as the result, we would get merge sort as gives you quicker or better performance. We would be more efficient using merge sort. So there are different approaches in sorting the data and also seeking a key value. That's what you saw, that's the beginning. Okay. The rest I just illustrated in table for the iteration, but if you understand the breakdown of this, right, then you can implement the programming side. So merge sort, cut it into halves until we can't cut it anymore to the least unit, which is 1. We would compare. If it's lower, right, put it in the order, merge, we order and then merge. Merge it all back to the original set size. Any question? So that takes care of the content we want to talk about today, right? So we talked about linear search. We talked about chunk or jump search. We talked about binary search. We talked about insertion and selection search, sort, insertion sort, selection sort, and merge sort. Okay. Then on Thursday, we'll work on creating these programs. So we're gonna have a quiz review next week, and then we're gonna have a quiz after that. So in Unit 9, then you have a quiz, but we have no quiz this week. So this week is just assignment and lab. Okay. Do you have any question for me? Something you're not clear on? Yay, I'm glad. So we'll look at C++. It's gonna be, you know, physically when you're seeing all these number movement and stuff, it's a little bit different. As I mentioned, that think about temporary position where you place your data as you move it, because you know, I tell it in my programming classes all the time, there's no magic place. Like you cannot put it in the air, right? Physically, when we move things, it's easier, but when in programming, you have to put it in a location and then, or you can point to a certain location and do that. Okay. Yeah, add your name, and I will add your extra credit for the ones that earn for the 10 points, and then I will share the posts for the solution. Many of you got it. Some of you gave me the matrix, which I asked for, but a lot of you went on and solved it, which is great. That's what I was looking for. Okay. All right. Have a good night. We are about 30 minutes early. Oh, I want to let you know that in the next couple of weeks, they might pop in live, but I think they're going to watch the video, but they will check out Canvas. You will get a survey for my performance as a faculty. I'm being evaluated for my 4th year, or going into my 4th year, and I'm up for 10 years. So you know, you can complete the survey. It's completely online, so they will email you the link. Please complete the survey and put your feedback. I read all the survey. I have my own course survey, so if I can improve in some area, I try to do that, and I change stuff up all the time to help make sure it's clear for the students. But that's coming in the next few weeks, so I just want to give you heads up. They might send you an email for that. Okay. And if you don't have any questions, I hope you have a wonderful night, and I will see you Thursday for the lab. Okay.
Good night. Thank you.
You're welcome. Bye.